The secret begins with division. Instead of relying on a few large points of attachment, the gecko spreads the work across an enormous number of microscopic hairs. Together, they combine attractions too weak to notice into a practical and controllable adhesive system, powerful enough, in theory, to support the weight of 2 adult humans. Geckos are not entirely alone in using this approach. Spiders possess a comparable system, but the gecko foot stands apart. From a distance, the most obvious feature is the broad pad beneath each expanded toe. Move closer, and the pad resolves into rows of flexible plates called lamellae. Magnify one of those plates, and its surface is covered by vast numbers of microscopic hairs called setae. Each seta then branches into still finer structures, ending in flattened tips known as spatulae. At every stage, the structure becomes smaller, more numerous, and more flexible. The broad toe divides into lamellae, the lamellae carry setae, and the setae divide into spatulae. The animal's weight is distributed across an immense network of tiny contacts. A surface that looks perfectly smooth is uneven at microscopic scales. Glass may appear flawless to us, but its surface still has tiny irregularities, preventing the molecules of the toe and the glass from being as close together as their visible contact suggests. Press a rigid object against glass and it will touch mainly at its highest microscopic points. Across most of the apparent contact area, minute gaps remain. A gecko's setae can bend independently, while their finer branches follow irregularities that a solid toe could never reach. This allows a much larger proportion of the foot to approach the surface extremely closely. Atoms and molecules are electrically neutral overall, but their electrical charge is not perfectly motionless or permanently uniform. Electrons are continually moving. At any particular instant, they may be distributed slightly more toward one side of a molecule than the other. This produces a fleeting electrical imbalance called a temporary dipole. One region becomes slightly more negative, while another becomes slightly more positive. That imbalance can influence the electrons in a neighboring molecule, creating a corresponding dipole there. For an instant, the 2 molecules attract one another. These weak, short-range interactions are commonly described as van der Waals attraction. They occur throughout ordinary matter, including between the molecules of a gecko's foot and those of the surface beneath it. The attraction between any individual pair of molecules is tiny. The electrical fluctuations last for extraordinarily brief periods, and their influence weakens very rapidly as the molecules move apart. Across an ordinary visible gap, van der Waals attraction provides nothing remotely like a useful foothold. The 2 surfaces must be brought extraordinarily close at molecular scales before it becomes significant. That is the central purpose of the gecko's microscopic hairs. They do not manufacture a unique force, and they do not produce a chemical adhesive. Their hierarchical flexibility brings enormous numbers of spatulae into intimate contact with the surface. One molecular interaction is negligible, but one spatula approaches many molecules. Each seta divides into numerous spatulae. Each toe carries an enormous number of setae, and several toes distribute the animal's weight across the resulting contact network. Every contribution remains weak, but together they get the job done. The crucial quantity is therefore not simply the visible size of the toe pad, it is the real contact area, the proportion of the 2 surfaces that genuinely approaches closely enough for intermolecular attraction to matter. 2 solid surfaces can look as if they are touching while remaining separated across most of their microscopic area. The gecko's foot closes those gaps at progressively smaller scales. Its lamellae adjust to the broader surface, its setae bend around smaller irregularities, and its spatulae create intimate contact at the finest level. But this creates another problem. If enough microscopic contacts can hold the animal to a ceiling, how does it move anywhere? The answer lies in geometry. Gecko adhesion is directional and mechanically controlled. The setae work best when they are placed against a surface and loaded at the appropriate angle, with force applied partly as shear, meaning parallel to the surface rather than directly away from it. As a gecko takes a step, it places and uncurls its toes so the setae make contact in the correct orientation. Loading the foot aligns the hairs and increases the number of spatulae contributing to adhesion. The foot becomes strongly attached not merely because it has touched the surface, but because the animal has arranged and loaded its microscopic structures correctly. To release the foot, the gecko changes that arrangement. It lifts and rolls its toes away from the surface in a distinctive motion often called digital hyperextension. Rather than yanking the entire pad directly outward and trying to break every contact simultaneously, It peels the toe away progressively. Peeling concentrates detachment along a narrow, moving boundary. Spatulae separate in sequence, dramatically reducing the force required at any one moment. A strip of tape behaves similarly. Pulling the entire strip straight away is difficult, but peeling it from one edge is much easier. The gecko's attachment is not identical to tape, but the mechanical advantage of progressive separation is comparable. Its foot is therefore a controllable adhesive device, strong when placed, angled and loaded correctly, but rapidly releasable when that geometry changes. Returning to the whole animal, 4 feet cannot function as static stickers. Climbing depends on a precisely timed cycle of attachment and release. While some feet support and propel the body, another is being peeled free, moved forward, and prepared for the next contact. Forces must also be directed through the limbs in ways that keep the pads properly loaded. The gecko holds its body close enough to the surface to avoid creating excessive leverage that could peel its feet away unintentionally. If one foot begins to slip, rapid changes in limb position and loading can shift force toward the remaining contacts. The tail may assist with balance and recovery, especially during sudden slips or changes in direction, although it does not provide the toe pad's adhesion. On rough surfaces, claws can also become important. Where deep irregularities prevent the spatula from forming enough intimate contact, claws may grip projections and crevices that the adhesive system cannot use effectively. Successful climbing is therefore produced by the entire animal. Microscopic structures, flexible toes, coordinated limbs, controlled posture, and rapid correction all working together. Nor can geckos adhere equally well to every surface. Performance depends on the scale of the surface roughness, the material involved, contamination, moisture, and the condition of the toe pads. A surface can be too rough for broad contact, while dust can coat the spatula and prevent them from approaching closely enough. Gecko feet do possess a degree of passive self-cleaning. During repeated steps, some particles are transferred from the setae to the surface, because they adhere more strongly to that surface than to the toe. But this is an effective tendency, not permanent or perfect cleanliness. Water produces an even more complicated picture. Depending on the gecko species and the material beneath it, a layer of water may interfere with intimate contact, or the foot may tolerate wet conditions to some degree. There is no universal rule that every gecko adheres normally to every wet surface. Adhesive pads have evolved independently in multiple gecko lineages. Evolution has arrived at similar hair-covered structures more than once, repeatedly exploiting the same basic mechanical opportunity. Divide contact into sufficiently small, flexible units, and weak molecular attraction becomes useful. Engineers have tried to reproduce that principle in dry, reusable adhesives, climbing robots, and gripping systems designed for delicate or unusual environments. Yet copying a gecko foot is much harder than simply manufacturing a hairy surface. The biological system combines several scales of structure with flexibility, directional control, rapid peeling, partial self-cleaning, and the movements of a living animal. And so the gecko hanging beneath a sheet of glass is supported by a chain of structures almost entirely hidden from view. The broad toe pad divides into lamellae. The lamellae carry setae. The setae divide into spatulae. The spatulae conform closely to the surface, allowing immense numbers of weak molecular attractions to act together. Direction and shear engage those contacts. A change of angle and a peeling movement release them. The gecko does not overcome gravity with one exceptionally powerful force. It coordinates millions of extremely weak interactions through remarkably precise biological engineering.